everyone, this is lecture video 27, and in this lecture we will be covering applied optimization, in which we will search for the best or the optimal value of a given function, and while doing that we will be using first derivatives. Okay, let's concentrate on this chart, which gives us the summary of the steps that should be followed while solving optimization problems. First of all, of course, we will read the problem really carefully and try to understand what is given and what we want to optimize, okay? And then we will draw a picture of the story. For example, read the first one. We want to find the maximum area of an isosceles triangle. This is an isosceles triangle, which has this fixed perimeter 10, okay? So perimeter 10. Perimeter means the sum of these quantities. Like if you put the height like that, then if you name these parts as y, so perimeter is 2x plus 2y is 10. You may create different isosceles triangles with the perimeter 10, for example, like this, or for example, like this one. But what we want is, we want to find the quantities x and y with this fixed perimeter such that the area is the maximum. This is an optimization problem. So we first understand the problem and we draw the picture. And then in this picture, we introduce our variables. And we also find a relation between our variables, an equation relating your quantities and identifying your unknown variable like this. And then we will try to write a function depending on the unknown variables. For example, the function that we want to optimize here is the area function, right? We want to maximize the area. So let's try to write an equation for the area function. Okay, area can be written as the base times height, right? YH, it depends on YH right now, 1/2 times base times height. But after writing an equation for the unknown quantities like this, we want to maximize this function. And in fact, we can do it if this function can be rewritten as a single variable function. What I mean is it depends on two variables now, h and y, but it is possible to write this function as a single variable function depending on just x. How this is possible, I will explain, but after writing your function depending on a single variable, which is explained in this item, then to maximize or to minimize it, to find its absolute maximum or absolute minimum, what you do, of course, you compute the critical points, you make a list consisting of your critical points and endpoints, and then you will evaluate your function at all the points in this list to choose its highest and smallest value as the absolute max and absolute minimum value. This was the technique that we have covered last week, which I called as the closed interval technique, right? So the main key point while solving the optimization problems are writing your function in terms of a single variable like this, and then finding the critical points, then proving that the absolute max or absolute min, depending on the problem, is attained. Okay, so we will follow these steps mainly. Okay, so let's try to finish the solution here. Okay, we write the parameter like this. We say we want to maximize the area. Now I'm interested in the area function, but it depends on two variables now. We don't know how to optimize functions of two variables. We need to write it in terms of just one variable. And from here, what you have, y equals 5 minus x, right? You see, we already write the y variable in terms of x. Okay, so area becomes 5 minus x, which is y. And is it also possible to rewrite h in terms of x? Yes, it is possible if you look at this right triangle and apply Pythagorean identity. you have this equality. So h can be written in terms of x like that, right? 5 minus x squared. Okay, this is the expression for h in terms of x. So let's also insert it to here. X squared 5 minus x squared like this. Okay, this is our area function. And in fact, we can rewrite it in a simpler way. If you compute this square here, it is 10x minus 25 square root. Okay, you see this is now the function depending on just single variable x, so that I can start the optimization process by first computing the first derivative of this function to find its critical points. Okay, how do you derivate this function? Be careful, it's a product function. By the way, right at this point, we can also give the upper lower bounds for the variable x, right? Obviously, since x is the length of an edge, it is something positive. And look at here, this part. If x is less than 5/2, then, if x is 5/2, this part is exactly 0. But if x is less than 5/2, it cannot, this part becomes negative, which cannot happen for square root functions. That's why instead of putting the 0 for the lower bound for x, I will put 5/2. Because to have a positive quantity here, x should be greater than 5/2. And here, of course, 5 minus x is the variable y, and y also cannot be negative. That's why x can be at most 5. You see, that's how you should decide boundaries for your unknown variable. And now we are ready to take its derivative. We want to find, let's write first, we want to find absolute maximum value of this area function over this interval. Okay, this is the exact same question that we were dealing in one of the previous weeks, right? So we know what to do. We first compute first derivative to find the critical points. Derivative of the first expression is -1 times the second expression plus first component stays the same times the derivative of the square root function. It is derivated as 1/2 times the square root itself times the derivative of the insider part, which is 10. Okay, so if you write both expressions over a common denominator, you can obtain this expression for the first derivative function. Okay, now we are ready to search for the critical points. Okay, we first compute the first derivative, now critical points. Okay, critical points happen when the first derivative is 0 or first derivative is undefined. Okay, a prime is 0 when the denominator is 0. From here, x is 10/3. And from here, what we have, a prime is undefined where the denominator is 0. So when this equation is satisfied, so x is 5/2. Okay, and these both are valid critical points because they both lie in this interval. Maybe I can also put equalities like this. Okay, so these are both valid critical points. I will take them in my list. Okay, now we are creating our list of special points. So x is 10/3, x is 5/2. Okay, and now the endpoints, x is 5. These two are coming from the critical points, and this comes from the endpoints of your interval. So now it's time to look at the images of those points under your area function. This 5/2 and 5. Okay, a 10 over 2 is this number. You can easily compute the images of your area function at these points. A5 over 2 is 0, and A5 is also 0. Look at your A function. A5 is 0, A5 over 2 makes this part at 0, and at this critical point, it gets this value. And among this list, you can easily see that this is the biggest value. So the absolute maximum value of the area function is this number, and it is attained at this x value, okay? So if you want to maximize the area of an isosceles triangle which has this fixed perimeter, you have, when you choose x equals 10 over 3, the area becomes the largest, and the value of the area is this number, okay? So in fact, this part is the first way of proving that the largest value of the area is attained. There is also the second way that you may prefer, which we call as the first derivative test. So in this second way, you will create a sign table for the original function, and then you can comment on the sign table for the first derivative function, and then you can comment on the original function. Okay, so it goes like 5 over 2, 10 over 3, 5. These are the critical points that we have. So between 5 over 2 and 10 over 3, first derivative takes positive values. You can easily check this by trying some value. And here it takes negative values. If first derivative is positive, A is increasing. If first derivative negative, A is decreasing. Meaning that something like this, some shape like this happens for your area function. So right at this point where x equals 10 over 3, you have an absolute maximum value for your area. Which value is this? It is this value, of course. So you can also use this kind of arguments that we call as the first derivative test to prove that at this point for x, the area becomes the largest. Okay, so let's move on and solve another example before we stop in this video. Next example, determine the area of the largest rectangle that can be inscribed in a circle of radius 4. So you see it, this is a fixed thing given in the question. It's an useful information. So the radius of the circle is 4, and this part is already named as 2x, so I can call this as x and this part as y, so that x squared plus y squared is 4. Okay, what we want to maximize here? We want to maximize the area of the rectangle. Okay, let's then write an expression for the area function. So area of the rectangle is given by, of course, this edge times this edge, where 2x times 2y. But as you can see, it is a function of two variables now. What we need to do to able to apply some calculus techniques on it, we have to eliminate one of the variables so that we end up with a single variable function. So let's try to write area function in terms of just x. Okay, it is then 4x times, is there a way to rewrite y in terms of x? From this equation, you can easily write, and by the way, it is 4 squared. So you can easily write y in terms of x like that, right? Okay, so 16 minus x squared. You see, now we have a function for the area depending on just x. Now we want to find what? Find absolute maximum of this area function over which interval? Now it is time to decide the interval for x. As x is a length, the lower bound for x is 0. And here, by looking at this component of your function, you can understand that x can be at most 4. Because if x exceeds 4, square root inside the square root becomes negative, which can never happen. Okay, so let's try to solve this calculus problem now. How do we solve that? We compute the first derivative to find the critical points, and be careful, this is a product function. You will be applying product rule. Derivative of the first expression times the second, plus first expression stays the same times the derivative of the square root part, which goes like that. Derivative of the square root is 1/2 times itself times the derivative of the insider part. Okay, then simplify things and then try to write everything in terms of over a common denominator. You can do that. If you do that, you will obtain this expression for the first derivative written over a common denominator. Okay, now I think after computing the first derivative, we are ready to find the critical points. Okay, they happen when the first derivative is 0 or the first derivative is undefined. First derivative becomes 0 if, look at the denominator, if this expression is 0, so x squared is 8. So x squared is 2 square root 2 or minus 2 square root 2, right? And look at the interval on x. X can be between 0 to 4. That's why you can directly eliminate this point because it is not in the interval for x. Okay, let's look at the second case where first derivative is undefined. So in this case, denominator is 0 when 16 minus x squared is 0. So x squared is 4 and then x is 2 or minus 2. And x squared is 16. Okay, 16 and x is 4 and or minus 4. And because of the same reason, you can directly eliminate the minus 4 point. Okay, now we have 2 critical points now. I will create a list of points. So this is the first way proving that the function takes its largest value. Okay, list of points. So x equals 2 square root 2 and x equals 4. These are coming from the critical points. Also, there is another one here. X is 0, which is the end point. Critical points, and this comes from the end point, so that this is a complete list now. And I will look at the values of my function at these spatial points like that. Okay, a of 2 square root 2. Here is your a function. Where is it? Yes, here it is. If you insert 2 square root 2 for x, you will find 32. And if you insert 4, this part becomes 0. If you insert 0, this part makes the function 0. So among this list, you see that this is the highest possible value, biggest possible value. That's why it is the absolute maximum value of the area function, and it is attained at x equals 2 square root 2. Okay, this is the first way of proving that your function attains its absolute maximum value at x equals 2 square root 2, and the absolute maximum value is 32. What is the second way? You can also create a sign table for the first derivative function by putting the critical values on your table like this. And okay, over here, your first derivative function gets positive values. After 2 square root 2, it gets negative values. You can easily check this by choosing some particular values over these open intervals. And then what does this tell you about the original function? Positive first derivative means that your function is increasing. Negative first derivative means that your function is decreasing. So some shape like this your function have, proving that right exactly this point, at exactly this point, your function gets its absolute maximum value. Okay, a of 2 square root 2, which is 32, is absolute max, is the absolute maximum value. Okay, you may either create a list of critical points plus endpoints, evaluate your function at all those points and choose the biggest, or you may try to construct a sign table like this. Okay, so let me summarize in a second what we have done, and then I will stop. To solve optimization problems, you will always in optimization problems, you will always have some fixed information like this. You will use that fixed information to write one of the variables in terms of the other one. Why do you need that? You need to do that because you need to write your function to be optimized in a single variable function. So one of the variables should be rewritten in terms of the other one, and this information will always be given in the question to you. Okay, after creating your single variable function, next thing is to do finding critical points. So to find the critical points, you have to compute the first derivative and then search for the critical points by searching for these two cases. After you find critical points, you can then prove that there is an absolute maximum or minimum depending on the question by using these lists and evaluating the image of your function at all the points on your list and choosing the biggest one. This is one way. Or you may create a sign table for your first derivative function, which then will prove for you that at some critical point, absolute maximum value occurs. Okay, so that's it. Thank you for your attention.